In today's Tute session, we are going to do a number of problems on drilling and milling operations. This is the equation sheet, the section of the equation sheet for milling operations. As you can see, up here we have got an equation which is used for relating cutting speed V to the spindle speed N. And we know what the difference between these two is. Cutting speed is the distance traveled by the tip of the cutting tool on the workpiece. And its usual unit is meters per minute. However, it depends on the unit that is used for defining diameter of the cutting tool, or parameter D. If in this equation D is in millimeters, then what we get for cutting speed will be millimeters per minute. If D is given in meters, then what we get for cutting speed will be meters per minute. And spindle speed always has got a single unit, and that is RPM, or revolutions per minute. Well, N is the rotational speed of the spindle, of course. And then we've got another equation relating feed rate to feed. If we have feed at hand and we have spindle speed available, then we can easily compute feed rate. The unit for feed rate is millimeter per minute, the usual unit, and also the usual unit for F, or feed, is millimeter per revolution. So F indeed is representing the amount of the feed motion against each revolution of the cutting tool, while feed rate is representing that same motion or feed against time unit, or that is often minute. We've got another equation down here which is used in order to compute machining time in the drilling operation, and that is the distance to be traveled by the tip of the cutting tool divided by the feed rate. The distance to be traveled by the tip of the cutting tool is T, that is the thickness of the workpiece material, plus A, that is considered here for the point angle of the cutting tool. As you can see, this much of distance, that is A, is to be traveled until full diameter of the hole is reached. And then the cutting tool has to travel all the thickness in order to produce a through hole. In case of a blind hole, then we've got to consider the depth of hole D plus this much of allowance in order to make the hole and achieve the desired depth of cut. And then there is another equation down here, that is the one that is used for computation of material removal rate. And in this equation, we need to consider diameter of the cutting tool as well as the feed rate, giving us the rate of material removal. And this is indeed an important parameter, because this is an indication of how efficiently we are performing the drilling operation. And machining time is always important, because time is money, and always machining time is something that makes a difference. Even a fraction of this time is important, because when we are producing, say, large number of parts, then a slight difference in machining time will make a difference in what we will achieve in the end. Okay, moving on to the first problem, homework problem indeed on say drilling. Let's see what we are supposed to do in this problem. It's asking us to consider a situation where a two-spindle drill is performing two holes, is making two holes on the workpiece at the same time. This is possible if we are making use of multi-spindle machines. And that was included in the, video clip. Let me just show you where it was. This is the scenario where we are dealing with a multi-spindle head. As you can see, this is a multi-spindle machine. It has got a number of spindles, and each one of these spindles is actually holding a cutting tool, and a number of holes are being produced at the same time. So this is the scenario in this given problem we are considering in this Tute session. There is a two spindle drill simultaneously drilling two holes. However, the diameter of the holes are not the same. That is, we are drilling a hole having a diameter of 1.25 centimeter and another hole with a diameter of 1.875 centimeter. And as you can see also in this figure here, the diameter of the two holes are not the same. However, the two drill bits move at the same time up and down, so both of the holes will be produced at the same time. The thickness of the workpiece material is also given, and it is this much, 2.5 centimeter thickness of the material. Both drills are twist drills with point angle of 118 degrees. So this angle theta is given, and that is equal to 118 degrees. This point angle is different for different drill bits depending on the type of the material being drilled. For most of the applications, for majority of the applications, this point angle is 118 degrees. Cutting speed, or V, is also given. So V, or cutting speed, is given. It is this much, 70 meters per minute. The rotational speed of each spindle can be set individually. What does that mean? It means that the rotational speed for this drill bit could be different from the other ones. So we can differently adjust each one of these as it is needed. So the spindle speeds of the two could be different. The feed rate for both holes must be set to the same value because the two spindles lower at the same time, and this is what I just explained. So these two move at the same time up and down, and then the feed rate is set to the total metal removal rate does not exceed this much. What does that mean? It means that the feed rate, the material removal rate resulting from machining by making use of these two drill bits cannot go beyond this reason. There is a limit, say for example a limit on the power available. So because of the limit on the power available, we cannot exceed this amount of material removal rate, which is resulted from action of both of the cutting tools. Now what are we asked to do? In A, we've got to compute maximum feed rate that can be used. And in B, we are asked to compute the individual feeds that result for each hole. And in C, we need to compute the time required to drill the holes. Let's do part A first. The maximum feed rate. What does maximum feed rate mean? It means that we cannot exceed this feed rate, and there is a limit for the maximum feed rate. What determines the maximum feed rate? The maximum material removal rate given right here. So we have got the maximum material removal rate given to us. We've got the diameter of the first hole and also diameter of the second hole. This is what we need in order to compute the feed rate. Now let's take a look at the equation sheet again. The equation sheet here, we've got an equation down here, this one, which is giving us material removal rate as a function of cutting tool diameter as well as the feed rate. Now question is that how can we make use of what is given in the statement of the problem and get the maximum value of feed rate computed? Okay, we take a note of this equation from the equation sheet and return to the statement of the problem here. Let's see what we can do. So we are after maximum feed rate and we are provided with maximum, say, material removal rate. If we take the equation for material removal rate from the previous slide or the equation sheet, then it gives us the possibility of relating maximum material removal rate to the feed rate. However, please note that there are two different cutting tools cutting at the same time. So what we need to do is to adjust the equation. That is, we take this equation from the equation sheet. However, the right hand side of it needs to be written two times. Once for the smaller, say, cutting tool, and once for the larger cutting tool. So we consider these two as D1 and D2. Now, this equation is giving us total material removal rate. What is resulted from the first cutting tool, from the action of the first cutting tool, and what is resulted from the action of the second cutting tool. And then we can rewrite this right-hand side of the equation in this form. So now we have got F, the values of D1, the diameter of the first cutting tool, D2, the diameter of the second cutting tool, and also we have got the maximum material removal rate. The only unknown parameter in this is now feed rate. So we can solve the equation for feed rate and then eventually get the value of the feed rate computed, which comes to this much. And that's the way of computing the feed rate in this problem on the basis of, say, maximum material removal rate. The only thing that we need to consider is that there are two cutting tools and the material removal rate for each of the cutting tools should be taken into consideration to get this done. Okay, now moving on to the next part of the problem, that is part B. It's asking us to compute the individual feeds that result for each cutting tool. And the unit of feed is also given here in centimeter per revolution. Also, the feed rate was computed in centimeter per minute as it was stated in the statement of the problem. Now for computation of the individual feeds, we've got to see what we need in order to get this done. Now let's get back to the equation sheet again. Okay, equation sheet here. We are after the individual feeds. The feed rate for both of the drill bits is the same, which is this much. However, the feed could be different and it is a function of the spindle speed. And it was mentioned in the statement of the problem that spindle speed could be set individually. So what we need to do is to compute the spindle speed for each of the spindles first. And once we have got the spindle speed for each of the spindles computed, then we can make use of this equation, substituting the values of feed rate that is already computed and also spindle speed for the given spindle to work out the feed for that given, say, cutting tool. And that's what we do. Now we make use of the first equation in the equation sheet, which relates cutting speed to spindle speed, and solve this equation for spindle speed. Well, cutting speed is given up here. We've got it, 70 meters per minute. It's given. The diameter for the smaller cutting tool is also given, and that is equal to 1.75 centimeters up here. And then once we have this at hand, we can compute the spindle speed for the first cutting tool. And similarly, if we substitute the diameter for the second cutting tool in the equation, we compute the cutting speed for the spindle speed for the second cutting tool. Now we take this equation out from the equation sheet. If we substitute the spindle speed for the first cutting tool, it gives us the feed for the first cutting tool. If we substitute the spindle speed for the second cutting tool, it gives us the feed for the second cutting tool. And these are all computed down here. Okay, no problem. Michael, I noticed that you went in and out. Not a problem, it's not disturbing us, so you can just join as when it is convenient for you. Do you hear me now? Do you have my voice? Okay, let's move on. Okay, good. Good to see you and good to have you with us. Okay, is there any question on this problem so far? Okay, part C, it's asking us to do the computation of the time required to drill the holes. Let's get back to the equation sheet. The time required for machining is given right here. So we take this equation from the equation sheet and then we just move on to the statement of the problem. It is asking us to do the computation of the time. In order to compute the time needed, we've got to compute the allowance right here, the amount of allowance that is needed, plus the thickness of the material, and divide it by the feed rate that is already computed. So we have the feed rate, we have the value of feed rate computed, which is right here. This is the feed rate, we have got it. Then thickness is given in the statement of the problem, and that is 2.5 centimeter. And then the only missing parameter in order to get this done is this parameter. How do we do this? Well, that's an interesting question indeed. There are two drill bits, and the allowance for this little one is different from the allowance for the larger diameter. The one that is greater is the one that should be considered, and of course it is the allowance for the larger drill bit, because they move at the same time up and down, and the extra travel for the larger drill bit is larger than the extra distance to be traveled by the smaller drill bit. So the distance to be traveled by the larger drill bit is the one to be taken into consideration. So what we do is just take make this triangle right here, this triangle, take it out, knowing that this is the right angle, knowing that the point angle that is 118 will be telling us about what is the angle in here, and then I'm going to show it in the next slide right here. So we take this triangle, right triangle here, we take it out and enlarge it. Okay, we know the value of theta, and that is 180. So it is very obvious that this angle here is theta divided by 2, and that is 118 divided by 2. Okay, now we have got a right triangle here. This little angle here can be easily computed if we have the value of theta at hand, and that is 90 minus this angle. And then we've got two sides of this triangle. The bottom side, this one, is the half of the diameter of the cutting tool, and we know the diameter of the cutting tool. However, we do not know about the side angle, which is this one, A. If we know a little bit of trigonometry, we can easily write this equation, which is relating the side angle to the other side, the side, and the length of the side of the triangle to the other side, and also the angle which is represented right here. So we can easily make use of this trigonometric equation and write this equation for the side of the right triangle, and that is dimension A. We can easily substitute the values of the diameter of the cutting tool as well as theta, and we have all this at hand. If we substitute this, we can compute the side of this triangle for both of the drill bits. For the smaller one, it comes to this much. For the larger one, it comes to that much. And if we take the equation for the machining time and substitute the values of thickness and the angle of the side of the triangle and the feed rate, then it gives us the amount of the time needed for machining of the workpiece in minutes, and we can also convert it into seconds. So we can then easily compute the amount of the time needed for machining of this whole surfaces. Okay, now let's move on to the next problem, which is on milling. We've got a number of equations on milling. A brief explanation on these equations. An equation up here which is relating cutting speed V to the spindle speed. Cutting speed is the distance traveled on the surface of the workpiece by the tip of the cutting tool. Spindle speed is the rotational speed of the spindle. So these two are not to be confused with one another. And we've got also another parameter sitting here, D, which is representing the diameter of the cutting tool in milling operations. If this D is included in meters, then what we get for V is meters per minute. If this is given in millimeters, then the unit for resulting cutting speed will be millimeters per minute. So we should take care of the unit of the that is used for representing diameter when we are using this equation. Another equation down here which is relating feed rate to feed. The unit for feed, which is also referred to as chip load, is millimeter per tooth. And the unit for feed rate is millimeter per minute. So these are different from one another. And also in the equation, what is included is the spindle speed, the one that we had up here, and also the number of teeth. of the cutting tool. In say milling operations, we are making use of multiple cutting edges. So the number of cutting edges on the cutting tool makes a difference in what we get for the feed rate, and that is important. Well, and then we've got material removal rate, which can be computed if we have the widths, depths, and also widths and depths of the cut as well as the feed rate. If we multiply all these to one another, then we get the material removal rate. As mentioned before, material removal rate is an indication of efficiency of the machining operation. So it is very important for us to achieve a high material removal rate in any machining operation. And then the last equation on this equation sheet, on this sheet of the equation sheet, on this page of the equation sheet is, say, machining time, which is computed if we divide the distance to be traveled by the cutting tool, if we divide the distance by the feed rate. The distance is the summation of the length of the workpiece to be machined plus an allowance or extra distance to be traveled. How do we get this? Let's take a look at the next slide, which is telling us what this is. Generally, there are two different or broad groups of machining operations. Those are referred to as peripheral or slab milling operations. The one that is shown here, where the axis of the rotation of the cutting tool is parallel with the surface being machined, like this one. If this is the case, then the amount of allowance can be computed by making use of this equation, which is the result which depends on depth of cut, D, which is shown here, depth of cut, and the diameter of the cutting tool, that one. If we have these two values at hand, then we can easily compute the value of allowance or extra distance to be traveled for milling operation in slab milling or peripheral milling. And what is this? It's shown right here, what the allowance is. If this is the direction of the motion of the cutting tool, cutting begins from this point. Still, the maximum depth of cut is not achieved. So this edge has to be traveled by this much. At this point, maximum depth of cut is reached. So actual machining begins before this center of the cutting tool is on the edge of the cutting tool. And this extra distance has to be taken into consideration if we are going to take a cut of this much. So the length of the cutting tool plus the allowance of A needs to be traveled by the cutting tool to perform this machining operation. In the case of face milling operations, where the axis of rotation of the cutting tool is perpendicular to the surface being machined. Now we are taking a look from the top view in here. This is the axis of rotation perpendicular to the surface being machined. In this case, we've got to make use of another equation for computation of the allowance or extra distance to be traveled, A. This is a function of diameter of the workpiece as well as the width of cut. So we have nothing to do with the depth of cut in this equation. Rather, we've got to take into consideration the width of the cut. The width of the cut for this cut is represented right here. It is different for different operations. It depends on the geometry of the workpiece and the cutting tool. And for this given operation, it is shown here. So we are just taking the cut from a portion of the top face and not the whole, say, top face. So the value of D is this much. And then the diameter also is another parameter which is playing a role in what the value of A is. So depending on the type of the operation, either it is face milling or peripheral or slab milling, we've got to make use of the right equation to get the value of allowance computed. Okay, is that clear what it means? How to make use of the right equation? If we do not know how to make use of the right equation, if we do not know what is meant by peripheral milling or face milling, then we may go for the wrong equation and get the wrong value. So it depends on the type of the operation. Peripheral and slab milling, this one, and for end milling and face milling, that one should be used. Okay, moving to the statement of the problem. It is asking us to machine the top face of a rectangular work part the top face of a rectangular work part is machined using a peripheral milling operation. The work part is 735 mm in length and 50 mm in width, and its thickness is also given to be equal to 95. So this dimension from here to here is 50, which is width of the cut. The length of the cut, which is this much, is given 735. This is the length. And the depth of the cut is also given. It is equal to 7.5 mm. That's the depth of the cut, which is given right here. The milling cutter diameter is given 60 mm, this one. And it says that it has got 5 cutting edges or teeth. The image that I have shown here is taken from somewhere else, so it's not properly representing the number of cutting edges given in this problem. However, the operation is the same operation, which is showing us there is a peripheral milling operation, and the cutting tool is also larger than the edge of the length of the cutting tool is greater than the width of the workpiece, so it can machine the whole face in one pass. Cutting speed is given, that is 80 meters per minute. Chip load. What is chip load? The depth of cut for each cutting edge is given to be equal to 0.30 millimeter per tooth. Depth of cut, as mentioned, it is 7.5. Now we are to compute the time required to make one pass across the surface. How long does it take for us in order to take one pass from the top face of this workpiece? And also, we need to consider 5 millimeters before and also 25 millimeters after the actual cutting, actual lengths to be machined. What does that mean? It means that we need to consider 5 mm on this side, from here to here, 5 millimeter extra, and also a greater length on the other side in order to clear the top face. So it comes to 25 in here and also 5 mm in the beginning. This is to be considered. So 2 extra distances are to be traveled in order to clear the face of the workpiece, and also we need to consider an allowance, which is this much. This also needs to be considered. So indeed, if we want to show it properly, I've got to take this 5 mm off from here and add this to this point here. So 5 millimeter in the beginning, 5 mm in the beginning, plus the length, plus allowance, plus another 25. So 4 different length components are to be taken into consideration. If we have all these 4 length components computed, then we can divide it by feed rate, and that will give us, say, the time required for machining of this workpiece. In order to do this, we just do it this way. First, we do the computation of the spindle speed in order to be able to compute feed rate later on. Because we know the cutting speed, we know the diameter of the cutting tool, we can easily work out spindle speed for this operation, which is this much. Then, by making use of the equation on the equation sheet, we can easily compute feed rate, because feed is given, which is chip load. Chip load is given. Number of cutting teeth, or NT, is given, and N is just computed. So we can compute feed rate accordingly, and that comes to this much. Now we have feed rate computed. If we know the total lengths to be traveled and we divide it by this feed rate, it gives us time. Okay, total lengths to be traveled is 735, which is the length of the workpiece, plus extra travels of 5 and 25. However, still we haven't computed the value of A, or say the allowance. If we get back to the equation for peripheral milling or slab milling, this is the equation. Okay, if we take this equation out and substitute the depth of cut, which is 7.5, and also diameter of the cutting tool, which is 60, then we can easily compute allowance for this given operation. And it is done here. 7.5, which is the depth of cut, 60 is the diameter of the cutting tool. It gives us this much, which is allowance. And then if we put all this together, it gives us total length divided by feed rate, gives us the time needed for machining of this pass, taking one pass from the top face of the workpiece. Okay, is there any question on this? No questions? Okay. And the next part of the problem is asking us to compute the maximum material removal rate. Okay. Maximum material removal rate. Okay, let's get back to the statement of the to the equation sheet that we have. Where did we have it? Here? Okay, the equation sheet here. It's giving us an equation for computation of the material removal rate. And I mentioned this before that this is important because it is telling us how efficiently we are performing the machining operation. In order to do this, we are in need of the width of cut. It was given that is 50. It was mentioned in the statement of the problem. Depth of cut 7.5 and feed rate is just computed. So we can take this equation out from the equation sheet and then do the problem easily. So we take the equation out from the equation sheet, substitute everything, and that will give us the material removal rate. A question that I'm going to ask is that what is meant by maximum material removal rate here? Look, it doesn't say compute material removal rate. It is asking us to compute maximum material removal rate. So what is meant by this word maximum here? Anything which comes to your mind? What is meant by maximum? Any ideas? Anything that comes to your mind? Okay, let me explain what it is. If this is representing the operation, as you can see, at this point, at the distance of A, when the center of the cutter is at the distance of A from the edge of the cutting tool, as this cutting tool touches the corner of the workpiece right here, a little bit of material is removed. So material removal begins at this point. And as this workpiece is moving in this direction, the rate of material removal rate increases. From just a small amount, it gradually increases. And at the point when this edge reaches to this point, which is just below the center of the cutting tool, then the maximum depth of cut is reached. And then maximum material removal rate is achieved. So it is asking us to compute the material removal rate when the maximum depth of cut is reached, and at that point material removal rate is maximized. And that's we already computed because we can see the depth of cut of 7.5, and that is the maximum depth of cut. So what we have computed here is already representing maximum material removal rate. Okay. Does it make sense? Okay. So that's it. So it is computed just like that. Okay, thank you very much. Is there any questions? That was the last problem that we wanted to cover in this Tute session. Is there any problems? Any questions? Okay. No problems, no questions. Thank you very much. Make sure you do all these problems at home in your own time. When you do the problem yourself, you do the problems yourself. It's the time when you face problems and questions. If you have got any questions, then you can ask me by posting it on the discussion area or next time in the next Tute session or at the Q&A session. Okay, that's all for today. Thank you very much for your participation, and I will meet you again next time.